When working with the sum of sequences, we can notice that certain sums appear more often than others. So it is good to know what are the values of those sums. We'll show here three such sums. The first one, which we already seen when we discuss properties of the sigma, is the fact that the sum of a constant is n times that constant, where n is the number of times that constant is added. So for example, if I want the sum from k equal 1 to 10 of 2, that means that I will be adding 2 10 times for every k from 1 to 10. And therefore, instead of writing this addition, we can replace it with multiplication. There is 2 repeated 10 times, and therefore this is 2 times 10, or 20. The second formula is a formula that gives us the value of the sum of the first n positive integers. The sum from 1 plus 2 plus 3 plus n is n times n plus 1 over 2. So for example, if I want to compute the value from k equal 1 to 100 of k, which will be simply the sum of the first 100 positive integers, I can use this formula with n equal 100 and say that this value of that sum is 100 times 100 plus 1 over 2. The 2 and 100 can simplify to give me 50 times 101, which is 5050. The third formula gives us the value of the sum of the squares of the first n positive integers. 1 squared plus 2 squared plus 3 squared plus n squared is n times n plus 1 times 2n plus 1, all of this divided by 6. So if I want the sum from k equal 1 to 100 of k squared, which is the sum of 1 squared plus 2 squared plus 100 squared, then again I will use the formula with n equal 100 and will write this formula as 100 times 100 plus 1 times 2 times 100 plus 1, all of this divide by 6. Immediately I can reduce 106 to get 50 and 3, and therefore the answer is going to be 50 times 101 times 201 over 3. If you do that multiplication and division, we'll have 338,000 and 350. The formulas B and C can be proven in using algebraic methods, but we'll do here just the part B, since the part C is a little bit more algebra heavy than part B. So we want to compute the sum of the first n positive integers, 1 plus 2 plus 3 plus and so on until n. Let's rewrite this sum in a order of decreasing values. So we'll start with n. The next value is going to be n minus 1. We are decreasing it by 1, n minus 2, and so on. And the last term in this sum written in that way will be 1. Now let's add those two equations side by side. The left-hand side is going to be 2s, and on the other side, as aligned, we'll add 1 and n, we'll add 2 and n minus 1, we'll add 3 and n minus 2, and finally we add n and 1. And therefore we'll have n plus 1 from the first grouping, and then we'll add to that the value of the second group, which is also n plus 1. and from the third it's going to give us also n plus 1, and so on, and the last one, or nth group, is going to be also n plus 1. Since we have n of those terms, then what we have is that 2s is equal n times n plus 1, and therefore s is equal n times n plus 1 over 2, which is exactly what we wanted to show.